Hi, my name is Jarrett Lewis, and this is my recording for homework number 1 for Transport 2 with Dr. Co. Alright, so we are given this situation. Oh, need to erase that. We have a capillary that is closed on both ends, filled with equal volumes of two ideal gases, A and B, with pressure P on both sides and volume V on both sides. The temperature is uniform and constant. Alright. And we know that the gas A has a molecular weight A and gas B has a molecular weight B. After some time, the barrier is removed and the gases are allowed to mix and become homogeneous, so that we have a completely mixed mixture of gases, alright, with the same pressure. Alright, so we can take the equations that we already know. So we know that the molar flux equation is just equal to the sums of the molar fluxes of each component gas. So component gas A and B are equal to the total molar flux. But we also know that the molar flux is equal to the molar concentration times the molar average velocity. Alright, we also know that the molar diffusive flux is equal to the molar concentration of A times the molar, or the mass average velocity of A minus the molar average velocity. And I'm writing this in terms of A because it asks in the homework. We want the relationship of gas A. And we're also doing it for the mass diffusive flux of A. So it'll be the mass concentration of A times the mass average velocity of A minus the mass average velocity. Alright, so we want to derive an equation for a relationship between the molar diffusive flux and the mass diffusive flux. So you want a relationship between the two. Alright, to do this, we gotta first look at how this mixing happens. So we go from here to here, right? A is on the left, B is on the right. We can say that for every 1 mole of A that is going to the right, there has to be 1 mole of B going to the left. And this is basically saying that there's no net molar flux. Our N is equal to 0. So, I'm just making sure I'm still recording. This means that we can set both of these equations to 0. And this is basically going to tell us that the molar flux of A is equal to the negative molar flux of B. And we can also set this one equal to 0. So the molar concentration times the molar average velocity. All right, and this one is saying that either one of these has to be 0 or they both have to be 0. And we know that the concentration cannot equal 0 because we have a mixture of 2 gases in a capillary. There has to be a concentration. So that is not equal to 0. So that means that this one must be equal to 0. The molar average velocity has to equal 0. So we'll just write that down. The molar average velocity is equal to 0. Alright, so now we need to look at our equation for the molar diffusive flux of gas A. So the molar diffusive flux of gas A is equal to the molar concentration of A times the mass average velocity minus the molar average velocity. All right, we already know that the molar average velocity is 0, so we can just get rid of that. We don't need to deal with it. And so we can rewrite this equation in terms of the mass average velocity, because we also have the mass average velocity here. It appears in both equations. It's the only variable that appears in both equations. So we can rewrite this the equation for the molar diffusive flux in that way. So we'll have the mass average velocity of A is equal to the molar diffusive flux of A divided by the molar concentration of A. So then we need to look at our equation for mass diffusive flux of A, which is equal to the mass concentration of A times the mass average velocity of A minus the mass average velocity. And we just set up here that the mass average velocity of A is equal to that quantity. So I'll put that in there, and then I'll distribute the mass concentration. So the mass diffusive flux is equal to the mass concentration of A times the molar diffusion flux of A divided by the molar concentration of A minus the mass concentration of A times the mass average velocity. And so we'll look here and see that we have the mass concentration divided by the molar concentration. And so if you take a look at the units for this, it looks like some mass, we'll say kilograms, divided by a volume divided by some moles per another volume. So these volumes will cancel out, and then we're just left with some kilograms per mole, which is equal to the molecular weight. So since we're doing them just for component A, it would be the molecular weight of A. So then we can rewrite the equation like this. We'll have the mass diffusive flux is equal to the molar diffusive flux of A times the molecular weight of A minus the mass concentration of A times the mass average velocity. So we have this in we included two terms that we were looking for, the molar diffusive flux and the molecular weight of A. Now we just need to deal with this second term here, which isn't in any terms that we can use. So first we need to look at the mass average velocity. In order to get rid of this, we're going to have to look at the definition of the mass average velocity for this binary system. And so it just goes back to the definition of mass average velocity. So we'll get that the mass diffusive flux of A is equal to the molar diffusive flux of A times the molecular weight of A minus the mass concentration of A times, and here's the definition for it, it'd be the mass concentration of A times the mass average velocity for A plus the mass concentration of B times the mass average velocity for B divided by the total mass concentration. And so we already have a relationship here that we described earlier for our mass average velocity. It is, so for any component, it would be the mass average velocity of that component is equal to the molar diffusive flux for that component divided by the molar concentration for that component. So it'll work for both components A and B. So we can rewrite that again. And then we will write it out. The mass concentration of A times the molar diffusive flux divided by the molar concentration plus the mass concentration of B times the molar diffusive flux of B divided by the molar concentration of B. All of that is divided by the mass concentration. And so then we have a similar situation as we did before up here, where we're dividing the mass concentration by the molar concentration, and this will become the molecular weight of A, and this will become the molecular weight of P. So we can rewrite that again. So we have the mass diffusive flux of A is equal to the molar diffusive flux of A times the molecular weight of A minus the mass concentration of A times the molar diffusive flux of A times the molecular weight of A plus the molar diffusive flux of B times the molecular weight of B, all divided by the total molar flux. All right, we are almost there. We just need to tidy this up a bit. So we can look at these two terms here. We have the mass concentration of A being divided by the mass concentration of the total mixture. And you'll get a unitless number from that, and that unitless number that we get is the the mass fraction, because we'll have the mass of A divided by the total mass of the mixture. So we can rewrite mass diffusive flux is equal to the molar diffusive flux of A times the molecular weight of A minus the mass fraction of A times molar diffusive flux of A times the molecular weight of A plus the molar diffusive flux of B times the molecular weight of B. All right. And then we identified something up here earlier, that the molar diffusive flux of B is equal to the negative molar diffusive flux of A. So we can rewrite that, because we already have the term for the molar diffusive flux of B. We want it in terms of component A. So we will rewrite mass diffusive flux is equal to the molar diffusive flux of A times the molecular weight of A minus the mass fraction of A times the molar diffusive flux of A times the molecular weight of A plus, that plus changes to a minus because we're switching the sign of it, minus the molar diffusive flux of A times the molecular weight of B. And now you can see that we have the molar diffusive flux of A as every term. So we're just going to clean this up, do a little bit of algebra, pull that out, and make it look nice and neat. So we'll have the mass diffusive flux of A is equal to the molar diffusive flux of A times the molecular weight of A minus the mass fraction of A times the molecular weight of A minus the molecular weight of B. And that is our final equation that describes the relationship between the mass diffusive flux and the molar diffusive flux. And it's written in terms of the molecular weight of A, the molecular weight of B, and the mass fraction of A. Thank you.